Hello, my name is Parker Greep, and welcome to the third of our recursive problems, Towers of Hanoi. Oh, that is embarrassing. Let me just exit out of that. This right now, just pause the video, go to mathisfun.com/game/towerofhanoi.html and play this game just so that you can understand what Tower of Hanoi is, and then come back. I'll wait. Alright, by now you should have a idea of what the game's about. You can move discs around, but you can't move the top disc onto... You can't move a bigger disc onto a smaller disc or else it doesn't work and you get this annoying error message. And the goal of the game is to get all of your discs from Tower 1 to Tower 3 in the minimum amount of time. So that would be this. Congratulations, you made a perfect game. So today we're going to be building a method that prints out all these steps to solve a Tower of Hanoi from an amount of disks. So we're just going to go over to Eclipse and let's just move this right here. Alright, that's a good size. Right here we have our static method called Hanoi, and it's going to return a big string that has all of our commands in there, and I'll show you how they'll be formatted in just a moment. And here we have our main method, which we'll be using to test out stuff. So right now we have our string of Hanoi, and the way we're going to solve this is we have to realize that Hanoi, to move this over, it consists of 3 steps. The first step is to move everything but the base to the middle peg. So this step right here, to take everything from on top of the base to the middle. The second step is to move the base over. And then the last step, step 3, is to just put our things over, and then that creates a perfect game. This is true with all of them. On disks 5, you will always have everything stacked up in the middle to move the base over. Same goes with 6 and everything above that. But first, before we split it up that way, before we do the first solution, let's just handle the base case, because normally we've always done the return statement first because that's been the easiest to understand, but in this case it's not easy to understand the return statement. So let's just start with the base case because that's the simplest aspect of our recursive problem. So if our number of disks is just going to be equal to 1, what we want to do is we just want to return a command that says from peg, and we'll just draw a little arrow signifying where it's going to go, to peg. And what we're going to do, I don't know why that happened, is after every single command, we're going to separate it with a semicolon, just so that we know when we have our final method how to separate it, how to separate each of our commands. And you'll see why we do that right at the end, and I'll show you why we have this semicolon. But this should return if our disk is 1. If we had 1 disk right here, let's just imagine that this is our 1 disk. This would return 1 to 3 with the semicolon afterwards, and that would be true. That would be true if this was a disk of 1. I actually have this up right here. Let me just reorganize all of this. Oh. So if this was a disk of 1, it would just move from here to here, and that would be the entire problem and all of it. Alright. Open both of these back up. Alright, now it's the more complicated stuff. I talked about the first step of Hanoi is just to move the top part to the middle. So we have to do that. Else, let's just initialize everything. We have our solution 1, which is to move this to here. We have our solution 2, which I'll talk about later, and our solution 3. Also, in order to understand where we're going, tower 2, since we only have from peg, tower 1, and tower 3 here, we're going to have to create something called the help peg. Int help peg, and that's going to be equal to 6 minus the from peg minus the to peg. And this should make sense because 6 is the sum of all of these towers together, so when the from peg is equal to 1 and the to peg is equal to 3, the help peg will be equal to 2. Because 6 minus 3 minus 1 is equal to 2. And this is just going to be an easy way for us to find the other peg. So let's say if we actually want to go from tower 1 to tower 2, our helping peg would be tower 3. Alright. Our solution 1 is going to be a recursive call. It's going to be the Hanoi of n disks minus 1. And we're going to be going from the from peg to the helping peg. And this should make sense because if we want to solve this, we have to move this amount. You have to pretend like this is a tower. And we have to move this from the from peg to the helping peg. And it's just that. Our solution 2 is going to be a string, and it's going to be, I believe it's from peg with the little arrow. It's going to go to to peg. So once we move all of these towers here, we're going to take a from peg, whatever's on from peg, we're going to move it over, and we're going to move it to tower 3, to to peg. Let me move this back. Alright. And finally, our solution number 3 is going to be equal to Hanoi, and we're going to move the n disks minus 1, and we're going to move them from the help peg to the to peg. And that should be step 3 because we just moved these. This is n minus 1 disks, so we'll move them up here. It's very theoretical, the solution to Tower of Hanoi, and if you try and draw it out, which I'm not going to do because it's so extensive, but if you take the time and try and draw it out, you'll see why it works. And hopefully, by looking at this, you'll understand why we split it up and why Hanoi n disks minus 1 works. We are just going to return all the solutions added up together. And because all the solutions are strings, it's just going to concat them right next to each other. And we will test this. Let me reset this. We will test this by creating an int number of disks. And let's just set that up equal to 3 right now. A string steps to solution. And we'll set that equal to Hanoi n disks. And we're going to create the from peg is 1 and the to peg is 3. By now you should have learned about advanced for loops, so I'm just going to create this right now. For every step in our steps to solution, alright. So what this will do is it will take every single what was I gonna say? It's going to take every single step, every single one of these, the from peg, to peg, help peg, to peg, whatever it is, that's separated by a semicolon. It's just going to print them out. So if we print this out right now, it should give us, oh, proceed. Oh, I did not save. Oh, what is this? Let's see why. 26. Oh, Strigna. What's Strigna? Oh, I misspelled string. Oh, that's silly of me. So now it should work. If I save it, it's going to give us this. So if I reset this one more time, 1 to 3, move this over. 1 to 2, 3 to 2, 3 to 2, 1 to 3, 2 to 1, 2 to 3, and 1 to 3. And that is going to work if we change the number of disks to like 5, and I bring this up to 5, exit out of this, and I start it up again. I'm not going to do all of these, but trust me, it does work. You'll just do all of them. There should be 31 steps here. There probably is. It looks like there is. So if I bring this back to 3, and so that is the solution to Towers of Hanoi. I really urge you guys to play around with this some more, and I want you guys to understand, try and draw it out on paper to see why these two multi-recursive calls work. Alright? And that's the end of this video.